I want to go through one more complete example where we find the Fourier series for a 2 pi periodic function. In this case, suppose that that 2 pi periodic function is one such that f of x is defined to be negative x from minus pi to 0 and 0 from 0 to pi. As I said before, my first thing that I want to do is graph this function, because if it turns out to be even or odd, I know that I'm going to be able to save myself a lot of time. So to do that, let's look at what's given, and then we can kind of extend it. So from 0 to pi, this function is just a constant y equals 0. And we're going to have that open here and closed here. And from minus pi to 0, I'm going to graph the function y equals minus x. So that's going to look like this. And again, this is closed, and then this ends up being connected here. And then I could extend this as far as I needed to using the fact that it's 2 pi periodic. But in this case, all I need is this to convince me right away that f of x is neither even nor odd. That's okay, but it just means that I can't skip any steps. And I wanted to go through one that's not odd and not even, just so we can really see all the detail. So I want to find the Fourier series. The first thing I want to do is start jumping into those coefficient formulas. So a sub 0 is 1 over 2 pi, the integral from minus pi to pi of f of x. We could split this up because it's piecewise, but notice that from 0 to pi, I would just be integrating 0, which is 0. So this really does reduce to just the focus of integrating from minus pi to 0, where f of x is defined to be negative x. So in this case, the antiderivative, so we'll have, the antiderivative of negative x will be negative x squared over 2. And then I'm going to bring in my 2 pi. So I'll write negative x squared over 4 pi. We are evaluating this from minus pi to 0 and plugging in my bounds. Take this negative 1 over 4 pi. I'm going to have 0 squared minus negative pi squared. And negative pi squared is just going to be pi squared. And I have two negatives multiplied together, so I get pi squared over 4 pi. And I can cancel a pi to get pi over 4. That's my a sub 0. So moving on to a sub k, we have 1 over pi, the integral from minus pi to pi of f of x times cosine of kx. And just like before, I know I can split this up because f is piecewise, but from 0 to pi, I would be integrating 0 times cosine of kx, which would be 0. So I can focus just on the integral from minus pi to 0, in which case I'm integrating negative x times cosine of kx. This is going to require integration by parts. So let's make sure we do that. So I'm going to have here u is equal to minus x, du is then negative dx. My dv is cosine of kx, and from our previous example, we talked about where this technically comes from u substitution, but my antiderivative is going to bring out a 1 over k, and then we have our sine kx. So that's my work off to the side here, and what I see then is that I have, my integral is now 1 over pi. I'm going to take u times v, so negative x over k sine kx, where we evaluate this from k equals minus pi to 0, minus a negative, so plus 1 over k, the integral from minus pi to 0 of sine kx. Okay, so one thing that I'm noticing right away is this first term in my square brackets. I have a sine kx, and previously when we looked at an example of Fourier series, we already noted that not only is sine of 0 equal to 0, sine of any whole number multiple of pi is also 0. So no matter what k is, when I try to find sine of minus k times pi, that's going to be 0. So plugging in either endpoint is going to result in this part being 0, which means, again, I can just focus on what remains. So in this instance, now I have my 1 over pi. I'm going to bring out another 1 over k when I antidifferentiate sine. So that's going to be 1 over k squared. And then the antiderivative of sine is going to be negative cosine kx. We're evaluating this from x equals minus pi to x equals 0. So at this point, what I can see is that my computation of a sub k, I'll label this here, a sub k, we now know is equal to negative 1 over k squared pi. And then I'm going to plug in my values here. So it's going to be cosine of 0 minus cosine of minus k pi. Now, I could write that as cosine of k pi or cosine of minus k pi. It doesn't matter. But again, I want to build off of what we learned in our previous example. We saw this same difference. So a lot of these things start to come up again. And what we observed is, first of all, we know that cosine of 0 is 1. And then we talked about, so I'm just going to write those as k pi. It doesn't matter. Cosine of k pi equals cosine of minus k pi. And we talked about the result that this depends on whether or not k is even. So in the instance that k is even, we have in parentheses 1 minus 1, so we get 0. But if k is odd, in parentheses we get 1 minus a negative 1, which would become 2. And if we multiply that by what sits out in front, we would get minus 2 over k squared pi. So this is my formula for a sub k. And just like we saw before, that means I'm going to have to take special care in expressing this in sigma notation. We can take what we learned before about how to remove the even k's from consideration. But before I do that, I still need to find b sub k. So finally, b sub k is defined to be 1 over pi, the integral from minus pi to pi, of f of x times sine of kx. Again, I can focus on evaluating f only from minus pi to 0 because from 0 to pi we would be integrating 0. So this becomes the integral from minus pi to 0 of negative x times sine of kx, which again is going to require us to use integration by parts. We let u equal negative x, du is negative dx, then dv is sine of kx, and v would become negative 1 over k cosine of kx. Using this, now I have 1 over pi, u times v, because we have a negative and another negative, u times v is just going to be positive x over k cosine kx, evaluated from minus pi to 0, minus, and then again I have 3 negatives here, and so this is going to be negative here, 1 over k, the integral from minus pi to 0 of cosine kx. Unlike my a sub k calculations, notice that the cosine term does not vanish at these values, so I'm going to leave that there for now and actually do this antiderivative we have over here. So we still have x over k cosine kx, and then anti-differentiating cosine of kx, I'm going to get, again, sine of kx, bringing out another k, 1 over k I should say, so we get 1 over k squared sine kx, and this whole expression is evaluated from minus pi up to 0. Now, the second term here has sine of kx, and we know again from our previous work that sine of kx is 0 when you replace x with 0, and when you replace x with minus pi. Oops. So I'm going to cross that out, and then we can just focus on what's left here. So at this point, I now know that b sub k is, I'm going to bring out that k, 1 over k pi. And then when I plug in 0, we have to plug it in for both places that we see in x. And then minus, when we plug in minus pi, so certainly this first term goes away because we're multiplying cosine by 0. And then we want to think about the remainder here. And what we can see is that this becomes 1 over k pi times positive pi, because I have minus and negative. And I can write this as cosine of minus k pi or just cosine of pi. But again, I can cancel a pi from top and bottom. And then remember that essentially what we've been seeing is that cosine of k pi is negative 1 to the k. When k is odd, cosine of k pi equals negative 1. And when k is even, cosine of k pi equals positive 1. So what I get from this is that my coefficient is negative 1 to the k divided by k. So you can see this process is very long when we see that all of the coefficients are non-zero. And then, of course, I still have to do the final part where I put this into the format of the Fourier series. So the Fourier series is, and I'll just as a reminder, because I haven't written it here, the general format we're looking at is what I'll write up here. And we just have to replace our coefficients with what we found them to be. Now, a sub 0, we said was pi over 4. So we just write that in there. Now, for the a sub k's, what we observed was for odd k's, we get this negative 2 over k squared pi. Again, I'm going to build off of what we saw in our previous example. We said that we can just get odd k's if everywhere we intend to write k, we instead write 2k minus 1. So that means I'm going to write my coefficient as negative 2 over the quantity 2k minus 1 squared times pi. So negative 2 over 2k minus 1 squared times pi. And I know that that sits in front of cosine of kx, but again, I'm going to replace this k with 2k minus 1. So that is the way that I get the pattern of just the odd index values. And again, the reason I am making this swap instead of putting k here is that we don't want to have any even k's because we determined that those all have coefficient 0. And then finally, it's a little bit easier to write this last one because we found our b sub k is just equal to negative 1 to the k over k. That doesn't depend on whether k is even or odd. We're saying for all k greater than 1, greater than or equal to 1, we're getting that pattern. So that means I can simply put that in place of b sub k, sitting in front of sine of kx. So in this video, we've seen a very complete process where we didn't have any shortcuts available to us. All of the coefficients were non-zero, and then we had to do the work of putting it into sigma notation.